Okay, so I'd mentioned this. So all of this stuff, we had said, when we talk about the central nervous system, we had said it receives information and it responds, but in between there, it receives information and then it integrates it. And what does that mean? That means it's deciding what to do. So neural integration is how all of these impulses are pulled together and used to make decisions. And so it involves a summation of all of the excitatory and inhibitory presynaptic partners, right? So you have all of this stuff coming in, and it's this sort of decision-making process. So I had mentioned that, when we were talking about hyperpolarizing, we had said it moves it, resting membrane potential minus 70. And if it was hyperpolarizing, you move it towards minus 71, minus 72. And then if it's depolarizing, excitatory, we had said it moves it from minus 70 towards minus 69 and so on. And we had said you have to get to minus 55. And so what that means is you need a net effect, summation, a net effect of positive 15 millivolts, right? So what effect does one excitatory impulse have? About a half of a millivolt, positive 0.5 millivolts. So if you have to go 15 positive millivolts, that means you need 30 excitatory impulses, but they're also being offset by inhibitory, so impulses that are pulling it the other direction. But if we were to sort of take a nerve cell in a vacuum, it would take 15 of the or 30 of those excitatory impulses to get you to, that's the minimum, to go from minus 70 to minus 55 millivolts. Okay. So when we talk about summation, we can talk about it from two different ways, right? So it can be, a one neuron sending an impulse one after another, after another, after another. And so that's a speed. That's a speed summation. It's called temporal. But then we said you got 10,000 presynaptic neuron partners when we talk about a motor neuron. So also, if you are involving more than one neuron, the summation would be what we call spatial. So and in reality, it's a combination of both. There's the speed that is being, that the nerve impulses are being received, as well as multiple partners, right? And so you have these partners, and some of them are the ones that are always pushing you towards action potential, and then you have the ones that are the standoffish kind, and they're inhibiting you, right? So you have these different groups of neurons, some of which are facilitating, pushing you towards just do it, and others are going to be inhibitors, presynaptic inhibitors. And so we have, lots and lots of these things. Okay, so how on earth I can close my eyes and I can see my grandma, right? I'm sure you can too. Where is the grandma in there? We've talked about the brain and how it functions. Where is your grandmother in all of this? All we ever said was that nerves produce action potentials at different rates. And how do you know? That's one side of it. And then how do you know where it came from? How do you know it's pain, or how do you know it's pleasure? And so we have, I'm going to talk about this pain versus pleasure thing first. And we'll talk about, that's what we call a labeled line code. So how do I know that the nerves from my eye that go to the back of my brain, to the occipital lobe, how do I know that they are light, and different light intensities and different colors? Well, that part of my brain looks and says, oh, that's coming from his eye, so it must be light. Now, how do we know that that's the case? You ever watch the cartoons? And in the cartoons, somebody will take a giant hammer and whack somebody else on the head, and they'll show stars flying around their head. That's not purely made up. If you've ever hit your head hard, you see stars. And why do you see stars? It's because you jolted your head so hard that it caused nerves in your retina, in your eye, to send a signal to that part of your brain, and your brain said, oh, must be light, and that's stars. So this is this labeled line code. Your brain looks to see, where did the signal come from? And so it's like people that have a heart attack. They sometimes will say, my left arm hurts, or their back hurts. Now, why are they doing that? Well, your heart doesn't normally hurt. And so your body, your mind, is saying, well, I don't know what this is. It must be my arm. Because sometimes your arm hurts, right? And so it's trying to figure out, where is the pain coming from? And it decides it's your arm instead of you had a heart attack. Somebody I know, when they had a heart attack, they thought they thought they had a toothache. No, it was heart. But that's something we call referred pain, and it's because it's not a pain that your brain has ever had to figure out, but it relates to this labeled line code. So the same part of your spinal cord where you have signals from your heart coming is also where you have signals from your arm. So you have this labeled line code that tells you what it is. Then you have some neurons that don't have many inhibitory presynaptic partners. And so, like, if we talk about something going on in my hand, and I can feel me touching my thumb, I can feel that. I feel it right now. Yeah, there it is. I got it. Or if I take pliers and I squeeze my thumb, I'm not going to do that. But there's a difference, right? So when I touch my thumb, it's a signal. The neurons that go to, the excitatory neurons that go to action potential easily say, yep, there's something touching his thumb. But then you have some that have a lot of inhibitory partners, and they only send their signal when you clamp down. And so at that point, I'd be, that really hurts, right? So you have this quantitative quality that comes from the nerves that rapidly go to action potential, along with the other nerves that take a lot of stimulation for them to go to action potential. All right, so that's how you know where the pain is, and whether it's a light caress or something really painful. It has to do with how readily the neuron goes to action potential. The last thing I want to talk about today has to do with memory traces. And I started to make reference to this a few minutes ago. I said, I can visualize my grandma. She's been dead for quite a while now. And so how is that? How is that done? And there's been some really cool studies where they use a system. I don't know what happened then. I just got a pain in my arm, my right arm, not my left. So what they do is they would have somebody watch a movie. So there's a study where they've had people watch a movie, and then they watch what's going on in their brain. And they watch, and I don't mean like the African Queen. I mean like a 30-second clip of an elephant running across the savannah. And so then they study what's going on in the brain when you are watching that. And then, they do a number of different, they've done a number of different things, maybe a clown juggling or whatever. And then what they can do, and so they train the computer. The computer is trained to see the memory trace that is associated with the elephant running across the savannah, in contrast to a clown juggling balls. I just made that part up, but the elephant is an example, true example from the study. And then what they do is they don't tell the computer what the person's going to see, and they show the person watches a video, and they have the computer generate what it thinks is going on from the memory trace. And unbelievably, you see a blob going across the savannah. And so what they've done with this study is they've been able to show that a memory trace is literally a pathway through your brain which is associated with imagery. And it's remarkable. It's remarkable because to me, I always kind of said, where is the movie theater? There's got to be a screen somewhere inside of there. No, there is no screen. It has to do with a pathway. Now, what is interesting is there is what we call a plasticity to this, especially old memories. Maybe you and a sibling have a memory that you share, and I can be talking about it, and my brother say, that isn't what it was. It was, way bigger than that. And one or both of us are wrong because these memory traces change over time, and it's why with memory, why they don't, in courts of law, eyewitness testimony isn't absolute, because sometimes people remember wrong. All right, so I've gone a little bit long, but I'm going to have to finish this up. I have a half a slide here. We have immediate memory, which is, it's a memory that you forget. You're just walking along, and you step here, you step there, you step there, and 10 minutes from now, I can't remember exactly where I stepped, but at the time, you know exactly where your foot was. It's memories that are irrelevant in the big picture, but you have it for a very, very short period of time. Step, 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 or, just routine, meaningless stuff. Then you have short-term memory. And this is the memory that lasts a few seconds or a few hours. Maybe somebody gives you a phone number and, 555-1212, and you say, oh yeah, I've got that. And then, a few minutes from now, I still remember it. And then 2 hours from now, I say, oh, darn it. What was that number again? And what happened is I haven't gotten it permanently stored away in my brain. And so with long-term memory is the kind of memory where you can remember many years later. My childhood telephone number. I remember it. Of course I do. It's completely unimportant to me now. I haven't had that number in 40 years, but I remember it. Now, so what happens when you're maybe a young lady or a man has given you a number and you want to remember it, you say, oh, think. Remember that number. 5551212. What is it? Okay. And so what you do is you train your brain. Long-term memory, you can train your brain to remember something, and you will remember it basically forever. It might change a little bit, as I said, plasticity, but you will remember it forever. It can be declarative or it can be procedural. Riding a bike. Once you know how to ride a bike, you always know how to ride a bike. You know how to tie your shoe without thinking, oh yeah, let's see, I go this across here, make a loop. You know, you just do it. You don't have to think about it in a verbal manner. You know procedurally. All right, I'm going to stop right here. It's going to take me forever to upload this. You guys have a good day, and I'll be talking to you again on Monday.